All right, so first, chapter 10 deals with stoichiometry. And what stoichiometry is, these are just quantity relationships. When we deal with quantity relationships, the easiest is by mole or molecule or formula unit. We could also do quantity relationships by mass, but it's a little bit more difficult. You'll see from the numbers we come up with. And so if we do it by mole, molecule, or formula unit, I could do this. I could do, for example, 1 molecule of methane, or 1 mole. Probably the easiest is 1 mole, because working with individual molecules is a bit of a pain. We'll talk about that when we look at the mass numbers. So I'll leave a little bit of room here. I'm going to write the masses there. So if we have 1 mole of methane, do you know how much 1 mole of methane weighs? Is that a number that's easy to remember? No. And so by mass is less convenient. So let's say is typically less convenient. There'll be some times where mass might be more convenient, but most of the time it's less convenient because it's hard to remember. If I have 1 mole of methane, you know, the average carbon atom, how much that weighs? 12.01. And the average hydrogen? 1.01. So 1.01 times 4 is 4.04 plus 12.01, that's 16.05. And so the average methane, a gram of mole, a mole of methane, if we just average it, it's going to come out to 16.05 grams. It's 16.05 grams per mole. And so it's 16.05 grams. That's how much. If I burn this in air, the oxygen in air will react to form what? What type of reaction is this? Combustion. And combustion reactions like this form, what is the product? CO2, carbon dioxide, and H2O. So we just remember the products of combustion of an organic compound like methane is CO2 and water. So if I have 16.05 grams of methane, you know, one of the reasons there's been talk about banning methane, you know, and do you know the reason why some people want to ban methane? Because of carbon dioxide. Carbon dioxide leads to UV or global warming. UV exposure or global warming? Global warming. So this is the reason why. It's gotten to the extent that some people are thinking they should, I don't know. They want to eliminate methane, but one of the big sources of methane would be cows. Cows produce a lot of methane. And so do you want to eliminate cows? Maybe the population might be decreased. But what people are thinking is not eliminating, you know. Maybe not the way to think about this is to eliminate the methane. Rather, keep the methane and then eliminate the product, CO2. So what can you do with CO2? Does CO2 burn? No, and so you can't really do much. It's already spent. As far as fuel goes, it's completely spent. You can't get any more. calories or joules out of, or whatever. Those are units of energy out of the CO2 by burning it. But there are other things you can do, and those other things would be to convert CO2 to kind of reverse it and convert CO2 into like methanol. You know, and that's already been done. And so these are things that people are thinking, or convert CO2 to something else. Chemically. But let's go ahead and figure this out. If I burn 1 mole of methane, do you know how many moles of CO2 will I have? 1 mole of CO2. But if I burn 16.05 grams of methane, how many grams of CO2 would I have? You see, it's a little bit less convenient. Because here, it's simple. 1 mole, 1 mole. And so I'll end up with 1 mole of CO2. But in terms of 16.05 grams, how much CO2 is that? How many grams? Well, 1 mole of CO2 weighs how many grams? Let's try to figure that out. So the average carbon weighs 12.01. What does the average oxygen weigh? 16 times 2 is 32. 32 plus that gives me 44. So 44.01 grams. And so we have these things that we call ratios. So for example, the mole ratio would be 1 to 1 mole ratio. But would the mass ratio also be 1 to 1? No, what is the mass ratio? The mass ratio is a lot less convenient. The mass ratio is going to be 16.05 to 44.01 mass ratio. Mass ratio, we can use it. Sometimes we do, but it's just less convenient. And so typically when we think about quantity relationships, we think in terms of the mole ratio. How many moles of O2 will I need? 2 is correct. How did you figure that out?
There's 2 oxygen atoms.
How you figure it out is we have to balance this equation. So this equation is not balanced, so let's go ahead and balance it. What I'd like to do is I'd like to save the single element ones for last. Because if I change this, CO2, it changes both carbon and oxygen. If I change this, it changes both carbon and hydrogen. So these ones we should do first. And so over here I have 4 hydrogens. And over here I only have 2, so I need to change this to what? H4O? Or 2H2O? 2H2O. And now the hydrogens are balanced, but it screwed up the oxygens. And so what I'll do here is I'm going to take these 2 oxygens and add these 2. That gives me a total of 4 oxygens. And that means we'll need to double this. And so now it should be balanced. And so methane's a gas, O2 is a gas, CO2 is a gas, and H2O is a liquid. And so the mole ratio is 1 mole of methane requires 2 moles of oxygen to react. And how many moles of water are going to form? 2 moles of water. So let's take a look at the masses. How much does the O2 weigh? 2 moles worth of O2? Yeah, it's 16 times 2 is 32, but I have 2 moles worth. And so I need to multiply by 2 times 32. And since I have doubled the number of moles, it's 32.00 grams per mole. And so this is 2 moles, moles here, moles cancel. So 64.00 grams. And how many grams of water is 2 moles? Again, this would be 2 times. Hydrogen is 101, so this 202 plus 16 is going to give me 18.02. $36.04. And so I could have mole ratios and mass ratios. And so let's look at mole ratios. Mole ratios in this type of stoichiometry, this is like 98% of the problems we do. We use mole ratios. And the mole ratios we can generate is if I have 1 mole of methane, then that's going to produce 1 mole of CO2, like that. Or if I have 1 mole of CO2 produced, then I must have used up 1 mole of methane. So I can generate a whole bunch of these, etc. And we can also generate direct mass ratios. In 2%, I only do direct mass ratios if I'm given the masses to make it easy. And so that would be 16.05 grams of methane produces 44.01 grams of CO2, or 44.01 grams of CO2 per 16.05 grams of methane, etc. Etc. because we could do this for any of these. Take a ratio between any 2 of these here. It's fine. And so direct mass ratios are less convenient. Molecule ratios are quite convenient here because we could either do it in moles of molecules, which is 6.022 times 10 to the 23rd molecules, or we could do it by individual molecules. So if I take 1 molecule of methane plus 2 molecules of oxygen, gives us 1 molecule of CO2 and 2 molecules of water. And so mole or molecule is fine. If it doesn't form molecules, we could use formula units. That's fine. But we have a problem with the mass. This becomes terribly inconvenient. Because if we do it by individual molecules, let's say you have a glass of water and you just pick one of the water molecules out of the water. It's like a raffle. What water molecule are you going to pick? Are all the water molecules in the glass of water exactly the same? What if you pick a heavier water molecule? Can you return it and grab a different water molecule? Yeah, I suppose you could just put it back in and grab a different water molecule. But it depends on this. So when we look at the mass of an individual molecule, we have to take into consideration this. Not all the methane molecules are the same. So for example, if I grabbed a methane molecule and it was this one, there are 2 isotopes of carbon. There's carbon 12 and carbon 13. Let's say, chances are I'll grab a carbon 12 because that's the most abundant. Like 99% of the carbons are carbon 12. And then there are 2 isotopes of hydrogen. What are the isotopes of hydrogen? Well, and then there are actually 3. H1, H2, and H3. H3 is radioactive, so we can ignore it. But H1 and H2 are the ones. H1 is much more common. That's why it's 101, 1201, 101. They're both like 99%. And so most likely, if I grab a molecule of methane, it's most likely going to be this one. And just about how much? Just approximately how much does this weigh? Doesn't have to be exact, but approximately it weighs about 16 U. We don't need to approximate the mass of carbon 12. You know exactly how much carbon 12 weighs. How much does carbon 12 weigh? 12. But hydrogen, that's not hydrogen 1. What is that? on the periodic table, it's not hydrogen 1, it's the weighted average of all the isotopes of hydrogen. What does a hydrogen 1 actually weigh? We don't read it off the periodic table, we have to go to the table of isotopic masses. Right? And so I'm not going to go to the table of isotopic masses. We're just going to say this one's going to weigh about 16 U. And then there are others, right? Another one would be with a carbon-12, but in this case, let's throw in a deuterium in there. So I could have this. It weighs a little different, right? So the mass of this one's going to be about what? About 17 U. So now when we do the mass relationships between individual molecules, we have to look at what molecule we picked out. Because I know the average. You know what the average methane weighs? The average methane weighs 16.05 U. You know, grams and U are the same, interchangeable. Right? But am I going to find a molecule in here that weighs 16.05 U? I'm not. It's like if you take a nickel and a dime, what's the average of a nickel and a dime? The average of a nickel and a dime would be like 7.5 cents. Is there a 7.5 cent coin? No, there's no such thing. And so in this case, there's no such molecule that weighs 16.05 U. And so if we're going to do this by molecule, then we need to know what molecule we're using. So how many different molecules are there for methane? So is this a unique molecule here? I'm going to move the deuterium to the top. Is this the same as this, or is it different? Same or different? They're the same. It's just like this. If I take, the clock handle moves, So if I take this and this rotated 90 degrees counterclockwise, it's the same. It's like they keep taking a clock handle. This clock handle was at, what is that, 3 o'clock. Now I move it to 12 o'clock. It's the same thing, so it's not unique. What would be unique is if I, let's say, threw another deuterium up here. Is that a unique molecule? Yeah, this one actually weighs about what? 18 U. Etc. There's certain things I could do that might make you think twice. So for example, is this one different or is this one the same? In terms of mass, it's going to be the same, right? It'll be the same mass. But now look at the position of the two deuteriums. Here I have one at 12 o'clock and one at 3 o'clock. Here I have 12 and 6. Do you see that? So is this different or the same? It's weird. Sometimes it's different, sometimes it's the same. It depends on the structure. This one, the structure of these turn out to be spherically symmetric. They turn out to be what's called tetrahedral. And oddly enough, these two are the same. You can't tell the difference structurally. And so if we put 3 deuteriums on there, it'd be different. Now, if it had a different structure, there's a different structure called square planar, then they would be different. And so we'd have even more molecules to deal with. But it's all right. This one turns out to be the same as that one. But that's something you learn in Chem 1A, not in this class. And so the next molecule would maybe have 3 deuteriums. And so how many possible combinations do we have? A lot. Too many. I don't even want to deal with it right now because there are going to be a lot. But for oxygen, we should be able to figure out how many. And so how many different oxygen molecules are there if given 3 isotopes of oxygen? And so let me do that over here. And the 3 isotopes of oxygen are oxygen 16, oxygen 17, and oxygen 18. Do you know which one's the most abundant? 16, 17, or 18? 16. And how do you know that? You would know that because the average mass of all 3 of those is not 17. If you average 16, 17, and 18, you'd expect the average to be right in the middle, 17. But the average is actually 16.00, 15.99.
How come it's like, in that table is 15.99, and there isn't like a 15 or 14 oxygen isotope?
Yeah, because oxygen 16, this weighs less. This is 15.994. The average is 15.999. And so the average is just slightly above the mass of this. It's approximately 16, but not exactly 16. And so the average, the weighted average is very close to 16. And therefore, that's the most abundant. And so the most abundant oxygen molecule would be an oxygen 16 attached to an oxygen 16. That would be the most abundant. The next most abundant, actually we aren't going to do this in terms of abundance. We're just going to figure out how many different ones we can generate. So how many different ones can we generate? We could have a 16-16, we could have a 16-17, we could have a 16-18.
17, 18.
Yeah, then we could have a 17, 18, a 17, 17, 18, 18. So how many is that? 1, 2, 3, 4, 5, 6. But what about this? Can't I also have a 17, 16? Or is that the same thing? It's the same thing, right? A 16, 17 is the same thing as a 17, 16 in terms of mass. But oddly enough, in terms of probability, this doubles the probability of finding that. But I'll talk about that. Well, I'm not going to talk about that at all. But we would say there are 6 unique molecules. And so depending on which of those unique molecules we pull, that's going to change its mass here. So probably the easiest is to use the average. Average masses rather than individual, but if we're doing this by molecule, then we want to know which individual molecule we have. Good. So 98% of the problems, we do it this way. So let's look at direct mass relationships first. And what we'll do is we'll look at direct mass-to-mass conversion. For direct mass-to-mass conversion, let's say in this example we're given that water contains 11% hydrogen by mass. And so how many grams of hydrogen are in 100 grams of water? I picked the numbers to make this problem easy to calculate. But 11% hydrogen means what? Yeah, this means 11 grams of what? 11 grams of H or H2? H2? When we look at H2, it looks like it's H2 because we have H2 here. But when we look at the H2, the hydrogens are actually bonded to oxygen, not to one another. And so this is not molecular hydrogen. In other words, does water contain molecules of H2 gas? Molecules within molecules? No, there's no H2 gas. If it did contain H2 gas, then Toyota would be very happy. You know, Toyota has the Mirai. Did I tell you about that? You fill it up with hydrogen. If water contained molecules of hydrogen, then it would be great. Just remove the hydrogen molecules from water, but it doesn't. Instead, we have atoms of hydrogen. And so what we have here is it's not 11 grams of H2 molecules, it's 11 grams of H atoms. So let's just say 11 grams of H per 100 grams of what? Of water, H2O. And so that would be the relationship here. So what we could do is we could do direct conversion. That is, if we start off with 100 grams of H2O, then we'll use the mass ratio as a conversion factor. The mass ratio would be 11 grams of H per 100 grams of H2O. And that gives us 11 grams of H. And so I picked this simple problem here.
Is this like the quiz problem?
What was the quiz problem?
250 milligrams of something.
Okay, yeah, that one's different. A little bit different. So in this example, we're given the mass ratio in terms of a percent. But it doesn't have to be a percent. The other way we could do the exact same problem here is we're given the mass ratio, or we calculate the mass ratio differently. So what we can do is we can go ahead and figure it out here. If I have, how much does a water weigh, a mole of water on average? A mole of water weighs 18.02 grams. This is a mole of water. And then how many moles of H2 are there in a mole of water? Well, H2, I shouldn't be talking about H2, I should be talking about H. How many moles of H are there in 1 mole of water? 2. So I have 2 moles of H atoms in 1 mole. In other words, what we do is we think in terms of the mole ratio because it's a lot easier. We know that there are 2 moles of H for every 1 mole of H2O. In other words, there are 2 hydrogen atoms for every 1 water molecule. And so this would be the mole or atom or molecule ratio. And then I know how much a mole of H2O weighs. A mole of H2O weighs 18.02 grams. That's the average per mole. And I know how much a mole of H weighs. How much does a mole of H weigh? Well, I know that H has an average mass of 1.01, but that's only to 3 sig figs. I want it to 4 sig figs for this particular problem. I want it to 4 sig figs because I want everything to 4 sig figs for my conversion factors. So, do you know the mass of H to 4 sig figs? What would it be? That would be it, or 1.008. So when I calculate the average mass of water, 18.02, I do it this way. The average oxygen weighs 16.00, and the average hydrogen weighs 1.01. So 2 times 1.01 gives me 2.02, and that gives me 18.02 here. And so for calculating the average mass of compounds, I use the average mass of hydrogen of 1.01. But if I'm just looking at H alone, or H2 alone, then I'm going to use 1.008. And so I have 2, and this is going to be times 1.008 grams. So 2 moles of H times 1.008 grams per mole. And so this is going to be, going to give me the grams of H per grams of H2O, and then I'll just multiply this. Actually, I'm not even going to multiply it. I'm just going to leave it like this. And so this is going to be 2.016 grams of H for every 18.02 grams of H2O. This comes out to 11%, which we had up earlier. And so the next example, we're just not going to use a percent. What we're going to do is just use the mass ratio as given. Because I want to save a step and not have to calculate the percentage. And then save another step by not having to get the fraction. And so what we'll do here in this particular example is we'll just do the same calculation. 100 grams of H2O, and then I see I'm going to have 2.016 grams of H for every 18.02 grams of H2O. And this is going to give me 11, I don't know, whatever it gives me. Let's calculate it. Should I have my calculator? So 100 times 2.016 divided by 18.02. 11.187 grams of H. So it depends on how many sig figs I want. If I just want 2 sig figs like that, 11 grams of H. That's what we expect. The reason I say this only happens like 2% of the time is because, we had to do some work to calculate that. So if this were given, then I'd do it like this. So if I were given the mass ratio, or if I was given the percent by mass, here, this is the percent by mass, which I could get the mass ratio from by going fraction here. Then I do this. Do a direct mass to mass conversion. But instead, and this is going to seem longer, we don't do a direct mass to mass. Instead, we typically do this. We start off at mass, and then let's say mass of A, it could be water. We go to moles of A, and then from moles of A, we go to moles of B, and then from moles of B, we can go to mass of B. And so we don't do it direct. Instead, what we do is we go through this, a mole-to-mole conversion here. A mole-to-mole conversion, this is the, you want to call the heart or the center or the core of the stoichiometry map. So what I mean by this is this is the core of stoichiometry. And so even though it seems like more work, because we're getting more steps, I mean this one was just a one-step conversion here. So if we go from mass to moles to moles to moles and then moles to mass, it seems like we're adding unnecessary steps there. But it turns out that this is, even though it appears to be more work, this is going to be better because of this. As the complexity of problems goes up, you know, and what the complexity usually involves different paths to get to the core here, and then different paths out. And so our initial map is this, and so this is the way I think about this in terms of an analogy. In terms of analogy, if you move to let's say a new city and you don't know the streets or anything, then what you want to do is you want to know where your home is, what the streets are, the cross streets for your home. And so this is going to be the core of your internal map in your head. And then what you do is you branch out further and further. But at least as long as you can return to the core here, or the center, then you know where you're at. And so what tends to happen is we get complex problems. These complex problems involve multiple steps to make it back here, and then once we're here, then we can exit out there. And so what we're going to do is we're going to do this for 98% of our problems. We're going to be using this. And so that's what I mean by that. Whereas these direct mass to mass are less convenient. I mean, these are harder to remember. Mole ratios are easy to remember. And so this is our home. And so an example of this would be doing it like this. So if we start off with 100 grams of water, water's A, and then what we're going to do is we're going to go to moles. So we have grams of water. We want to go to moles of water. How can I go to moles of water? Yeah, I know about how much a mole of water weighs. How much does a mole of water weigh? 18.02 grams. Okay, so the grams of water cancel, it gives us moles of water. And now I'm at the heart of the stoichiometry map. And what we do next is a mole-to-mole conversion using a mole ratio. The mole-to-mole conversion using a mole ratio is for every 1 mole of water, how many moles of hydrogen do I have? Yeah, there are 2 moles of hydrogen for every 1 mole of water. And so the moles of water cancel, and then I'm going to go to grams. That is 1.008 grams of hydrogen atoms per mole of hydrogen atoms. And what do we get here? The moles cancel, that leaves us with grams, and we're going to end up with 11.187 grams of hydrogen. So the situation here is the percent by mass, or the mass ratios typically aren't given, but the mole ratios are, in a problem. The mole ratio is given either from the formula, so this is the heart of our stoichiometry, the mole ratio, from the balanced equation or formula. In this case, this mole ratio came from the formula. There are 2 hydrogens for every water. There's 1 oxygen for every water. 2 hydrogens and 1 oxygen for every water. Or formula, as in this case. And so mole ratio is easy. Mass ratio is harder, I think, to come up with. So I did get the mass ratios for the combustion of methane, but we aren't going to use those mass ratios. Instead, what we're going to do is we're just going to do a mole-to-mole conversion for any problem involving the combustion of methane. And so in this next example, people are worried about combusting methane. They want to get rid of gas appliances, 1 pound of methane. So for example, I think the city of Los Angeles and the city of San Francisco have already banned gas appliances at new construction, like new restaurants and stuff. I'm not sure if they pushed it to residential. So they might have to go all electric, but there's concern about the electric grid, if it can handle that much. But if we burn 1 pound of methane, how many pounds of CO2 are generated? So if I burn a pound of methane, am I going to generate 1 pound of CO2? No, because I know the mole ratio. So for example, if I burn 1 mole of methane, how many moles of CO2 is that? 1 mole of CO2. So the mole ratio is not a big deal. But the mass ratio is, if I burn 1 pound of methane, do I have the mass ratio memorized? How many pounds of CO2 is that? I don't. Do I want to figure it out? No, I don't really want to figure it out either. So what I'm going to do is I'm just going to go to the core. The core of stoichiometry is a mole-to-mole conversion, and I can do a mole-to-mole conversion here. For every mole of methane, we get 1 mole of CO2. And then all that's different is I change how I get there. And so most problems would start off like this. So I'm going to do exactly 1 pound of methane. So I need to get to, I need to get home. I'm a bit lost, like in the new city, and you want to get home. That's your goal. And so the closer I get to that goal, the mole to mole, then the better off I'll be. So if I'm starting off 1 pound of methane, where should I go next? To grams. And so this one, you might have memorized or you might not, but it's 453.6 grams per pound. And so now I have grams of methane. And so now I'm kind of towards the core as I want to do a mass to mole conversion. And so 1 mole of methane weighs about how much in grams? 16.05 grams. It's just the average. The average is fine here because we have so many methane molecules. We don't have to worry about each individual one. But the grams cancel and the methane cancels, and that leaves us with moles of methane. And then from moles of methane, we're going to go to moles of CO2. And from the balanced chemical equation, it's for every mole of CO2, we had 1 mole of methane. And then it was balanced. And so the moles of methane cancel. And then we can go to grams of CO2. It was 44.01 grams of CO2 per mole of CO2. Okay, so the moles of CO2 cancel. That leaves us with grams. And I want pounds, so I'm going to have to convert grams to pounds. So 1 pound is equivalent to 453.6 grams. And so the grams cancel. And that leaves me with pounds of methane. And so the heart of the stoichiometry map is this mole-to-mole conversion here. And oftentimes we have to do a gram to mole, mole to mole, mole to gram conversion. Not always, but often. This is very common. I had to do an extra step because I wasn't given grams. I was given pounds. But let's take a look at what else might cancel. What else might cancel here is the 453.6 here in the numerator cancels this 453.6 in the denominator. So it looks like it's just going to be 44.01 divided by 1605. So let's do that. 44.01 divided by 16.05. I get 2.742. Okay, how many sig figs am I allowed? If I start off with exactly 1 pound of methane, how many sig figs am I allowed in my final answer? 1 because of what? Which? Well, how many sig figs here? Infinite? Not, well, the whole thing. 4? 4? Infinite? 4? 4. So I'm allowed 4 sig figs. If you're allowed 4 sig figs, I'm going to carry an extra one. I'd like to see how you rounded this. So this is 2.742 pounds. We're going to drop the 0 from CO2. Okay, so if we burn a pound of methane, we're going to produce 2 3/4, roughly, 2 3/4 pounds of CO2. That's a lot of CO2. Did that violate conservation of mass? I mean, I'm only starting off with 1 pound. How am I getting 2.72 pounds? Is like, am I creating mass out of nothing? No, where does that extra mass come from?
Well, oxygen.
From the oxygen. Right. The extra mass comes from the oxygen. So, so let's do this next calculation. In the next example, I'm going to burn 1 pound of methane, exactly. And then how many pounds of oxygen are required for this? So can you do this calculation? Did other people get this? 1.994? You got a different one? What did you get? 3.988? Yeah. Well, let's see this set up here. So you went to moles, is that correct? Of methane? 16.05 grams of methane. And then here's the mole to mole conversion. And what was the mole ratio?
2 moles of oxygen.
Yeah, 2 moles of O2 per 1 mole CH4. And so that gives us moles of oxygen. And then, how much does a mole of oxygen weigh? 32.00 grams of oxygen per 1 mole of oxygen. This mole ratio, I don't change it to 2. Some people change it to 2, but we don't need to. I don't need to cancel out the 2. Yeah. If I change this to 2, it'd be 64, but it's already going to be that anyway, so you get the same answer. And then to pounds. 453.6 grams. And this you got 3.998? 988. 3.988. Give me the 5th digit. What was the 5th digit?
It was 3.987.
Oh, it's 9875. All right, when we have a 5, do we round down or round up? Because 5 is right in the middle. So we could either round down or round up. And the rule is to round up. Even though it's right in the middle, we're just going to round this one up. And so this will be 3.988 pounds of oxygen. Oxygen's O2. We're using oxygen gas. And so this is what we have so far. We have methane plus 2O2 yields CO2 plus 2 waters. And so we have 1 pound of methane, and that's going to require 3.988 pounds of O2. And this is going to produce 2.74, actually I erased it, no I didn't, 2.742 pounds of CO2. So it doesn't seem to add up, right? Altogether, the total mass here is 4.988 pounds. And so I seem to be missing mass here, but that missing mass is in water. So can you repeat the calculation for water? Tell me how many pounds of water we have. So the next calculation you can do is when we burn 1 pound of methane exactly, how many pounds of water approximately do we get? Is it 2.245 pounds of water or 4.491 pounds of water? And so one quick check is this. They have to add up. So could it possibly be 4.491 pounds? And so the total atoms that you start with, I have about 4.988 pounds of total atoms that we're starting here. And the atoms don't disappear, they just rearrange. And so is it possible that this is 4.9, almost 5 pounds? If this were 5 pounds of water, then altogether this is going to be about 7 3/4 pounds of product, and it doesn't add up. So immediately we can eliminate this one's got to be in error, but I don't know about this one though. Could this one be correct? We don't normally check it this way. Normally when we check it, we just repunch in the numbers and see if it worked out. But let's see if that one, 2.245 pounds. 2.245 pounds. And so I'm going to add those two numbers up. I'm going to take 2.742 plus 2.245. I got 4.987 pounds. So we lost some. It looks like we lost some. We started off with 4.988 and then we lost some. Or did we? Did we lose some atoms? How can you explain this? Loss in mass. Rounding error. Yeah. I mean, this has got to be due to rounding error. That's it. I mean, we didn't lose any atoms. All the atoms should be there. So this looks like an okay match here. So conservation of mass, still good. All right, so we have the mass ratios. The mass ratios would be 1 pound of methane, 3.988 pounds of oxygen. Is going to produce 2.742 pounds of CO2 and 2.245 pounds of water. I would use the mass ratios if their masses are given. You know, if they're given like this, then I'll use it. Then let's say I had 3.68 pounds of methane. If I have 3.68 pounds of methane and I have the mass ratios here, then I'll just convert it to whatever I want in one step. You know, but do you want to do that for each problem? Do you want to go from the mole ratio and then get the mass ratios and then use the mass ratios? No, we don't want to do that. What we're going to do is we're going to just do it as a mole-to-mole conversion. It's going to make your life easier, and it's you want in an unknown city, you want something familiar, and that familiar thing will be, you know, your home. That is at the core of the stoichiometry map. The stoichiometry map, you know, is like your home, and then, you know, these problems are going to branch further and further out from home. And the further and further out from home, you know, the easier it is to get lost. But eventually, if you can make it back, then you should be okay. So let's try a different problem here. And that is other branches. So at the core is the mole of A to mole of B conversion. And so that's what we were doing, moles of A to moles of B, A whatever, B whatever. And the usual branches like mass of A to moles of A, moles of A to moles of B. But what we can do is we can go to, from moles, we can branch out to number of B. So what relates moles to number of units? So if I have a mole of CO2 molecules, how many CO2 molecules is that? That's 6.022 times 10 to the 23rd moles of CO2 molecules. So let's say B is CO2. What I need here is I need Avogadro's number. You know? And so rather than going to mass, let's say we start off at mass of A, and then we could go to moles of A. Then I use the molar mass to do that, or the molar mass relationship. And typically, if I go from moles of B to mass of B, or grams of B, you know, then I'll do that. And here we'll need the molar mass. But if I branch up like this, then I'll need Avogadro's number. Avogadro's number. So let's try a particular problem. If I burn 1 mole of methane, or not 1 mole, let's burn 1 pound of methane. Exactly. How many CO2 molecules did I just release into the air? It's not 1 mole. If it were 1 mole, it'd be easy. If I burned 1 mole of methane exactly, then I produce 1 mole of CO2, and 1 mole of CO2 has 6.022 times 10 to the 23rd. Right? But we're going to have to do a little bit of extra work for this one. There are different ways we can do this, many different branches. So for example, if we went from pounds of methane to grams of methane, grams of methane to moles of methane, we could do this. We could go from moles of methane to number of methane molecules. And then from number of methane molecules, we could go to number of CO2 molecules, because for every molecule of methane, I'm going to produce one molecule of CO2. It's balanced that way. So there are additional, pathways. This is like, the taxi drivers in London. I heard they have to pass a test. They have to have like the entire street map of London memorized. Have you heard that? Which is apparently very difficult because a lot of streets in London. And that way they have to be able to navigate different paths from one location to another, via different routes. And so it's the same thing here. Eventually we're going to have to navigate many different paths. So we'll start building our map bigger and bigger from here. And so this is an additional branch. This branch is the number of molecules, formula units. This particular branch. Did somebody come up with the answer? What did you get, Shane?
1.6996 times 10 to the 25th molecules.
Okay, anybody else?
I got 1.702
Times 10 to the what?
to the 25th.
A difference like this may not be due to rounding error. This is a more significant difference. Well, maybe not. This could be due. But if you're using the same conversion factors, I don't know what it is. Did anybody else
I used that.
get a different answer? Let's calculate this then. So what I did was I went to pounds to grams, and then grams of A to moles of A, moles of A to moles of B to number of B molecules. And so the calculation is going to be 453.6 divided by 16.05 times 6.022 times 10 to the 23rd. And I get this. I get 1.7019 times 10 to the 25th. Do you-
I'm not sure of my
Okay.
calculations. I got the second answer as well.
Okay, molecules. And then we round it to that, the 4 sig figs. And so 1.7 times 10 to the 25th, a lot of molecules. More than a mole's worth of CO2 molecules. Okay, we'll look at another branch, but before that, let's go on a break right now, and then we'll take a look at another branch after the break. All right, the quiz that you had with the heavy water, that one is a couple more branches or a couple more steps in here, but we can talk about that. Just work on that. That one's pretty challenging. But let's let me go on with another branch here. So for the quiz, it's a little bit different, but we can have our mixtures. So it depends on the composition of the mixture. There are two ways that mixtures are, at least the compositions are given. One way is percent by mass. The other way is by percent by mole or molecule or formula unit. And that's going to dictate how you do a particular problem. So let's say if we're given the grams of a mixture. So this is not puree. Over here, this is puree. And so how do we go? So from grams of a mixture, we would go to grams of puree. And from grams of puree, then we could go to moles of puree. But in order to go from grams of a mixture to grams of puree, we need the percent by mass. Sometimes we have the percent by mole. And so what we might end up with here is like moles of a mixture or molecules of a mixture. So an example of this would be air. You know, if I have 100 molecules of air, do you know roughly how many molecules of nitrogen and how many molecules of oxygen I have? No, you'd need a little bit more information. But let's say if I had 100 molecules, if I knew how many molecules of oxygen I have, then like air is a mixture of oxygen with other stuff. And then I can figure out how many of those are oxygen. And so for this, I would need the percent by mole. And that would take me straight to moles here. And so for air, I know this. Do you know how much oxygen is contained in air? Air is about 22% oxygen and about 78% nitrogen. Roughly. But the question comes up, is this percent by mass or is this percent by mole or number? Mole is just a number. And what would you think? Percent by mass or percent by number? Because that's going to dictate how we do this. In other words, is this 22 grams of oxygen per 100 grams of air? Or is this 22 moles of oxygen per 100 moles of air? And it turns out that this is by mole. And so in other words, if I had 100 air molecules, 100 molecules of air, how many molecules of oxygen do I have? I'd have 22 molecules of oxygen and 78 molecules of nitrogen. So we're given this, and so what I want now is this. Let's calculate, if I have 1 pound of methane, how many pounds of air do I need to burn 1 pound of methane? You know, not all the air will burn because air only contains 22% oxygen by mole. And so there are two routes we can take to get to the heart of the stoichiometry map. The two routes are we can figure out, well, this. I'm going to kind of go backwards here. In other words, the two strategies I have are like this. I'll start off with pounds of methane, and then from pounds of methane, I could go to grams of methane, and from grams of methane, I'm going to go to moles of methane, and then from moles of methane, I'm going to go to moles of oxygen, and then from moles of oxygen, I'm going to either branch out to moles of air, or I'm going to branch out to grams of oxygen, and then to grams of air, to pounds of air. And so this is the map we'll generate for this. If I go to moles of air, then what I have to do is I have to go from moles of air to grams of air. In order to go from moles of air to grams of air, I need the molar mass of air. Do I have the molar mass of air? I don't have that. So this branch, I need that. Actually, we can figure it out. But this branch, what do I need? To go from moles of, I have the molar mass of oxygen. That's not a problem. But what I need here is I need the percent by mass. Air. So the percent by mass for air we can look up, or it's given in the problem. Unfortunately, they didn't give it to us in this problem, and most people know the percent composition of air by mole, not by mass. And so what we're going to do is we're going to do a calculation. So basically we need just the mass ratio. We need the mass ratio between oxygen and air. But I don't have the mass ratio. I know the mole ratio between oxygen and air. And the mole ratio is that I'll have 22 moles of oxygen for every 100 moles of air. I know how much 22 moles of oxygen weighs. How much does 22 moles of oxygen weigh? Yeah, I just, this would be 32.00 grams of O2 per mole of O2. So eventually what I'm going to get is I'm going to get grams of O2. But what I need here is grams of air. But I don't have the molar mass of air, or do I? So one of the things I can do is this. What does air consist of? Air consists of 22 moles of oxygen plus how many moles of nitrogen? 78 moles of nitrogen. And 22 moles of oxygen, I can figure out how much that weighs. 22 moles of oxygen at 32.00 grams of oxygen per mole of oxygen. That's going to give me how many grams. So 22 times 32. 704. So I have 704 grams of oxygen. That's this, 22 times 32, that gives me 704 grams of oxygen. And then all I need to do is add this to how many grams of nitrogen I have. So if I have 78 moles of nitrogen, then each mole of nitrogen weighs how much? Well, the average mass of nitrogen is 14.01. And so it's going to be 28.02, just double it. And so 28.02 grams of nitrogen per mole of nitrogen. And so that's going to be 78 times 28.02. That gives me 2,185.56 grams of nitrogen. This is 704.00. Right? All right, so I add these two together, plus 704, and that's going to give me 2,889.56 grams of air. So I could use this as a mass ratio. Or I can convert that to a percent. That is for, as far as percent goes, it's 704.0. Actually, I'm not allowed this many sig figs. I'll just do 704 divided by 2889.56 times 100%. And I get 24.36% O2 by mass. So air is 22% O2 by mole. And so 22 out of 100 molecules of air are oxygen. But the oxygen weighs a little bit more than nitrogen. Oxygen weighs 32, nitrogen weighs 28. So oxygen's a bit heavier. And so the molecules are heavier. So even though I have 22 out of 100 molecules as oxygen, the mass percent is a little bit higher. It's 24 grams out of 100 grams will be oxygen. And so I could either leave the mass ratio like this, or I can clean it up by going as a percent and then do mass ratio like this. It would be 24 grams of oxygen per 100 grams of air. I'm just going to do this to 2 sig figs because to 3 sig figs the number is a little bit different.
I'm a little confused. We used the number that we got for nitrogen, like 2,185.56 for air.
Yeah, and so I add these two up, and that gives me the total grams of oxygen plus the total grams of nitrogen. Yeah. And the mixture we're just assuming contains only oxygen and nitrogen, so this is going to give me the total grams of air, which is 2,889.56 grams of air. And so if I add up all the pieces of air, then I'll get the total mass of air. So I'm adding up the pieces of air, oxygen and nitrogen, to get the total mass of the air. So I can now do this. This is usually given. You know, we could look this up online, or it's given. But instead, what we did was we calculated it here, just to show an example of calculating percent by mass composition. from the percent by mole. Because when I say this is usually given, but most people know this, or not most people, many people know this, have memorized this. If you have that memorized, then we can use that to figure out the mass percent, because I didn't have this memorized. Does anybody have this number memorized? Air consists of 24% oxygen by mass. Nobody has this memorized. Everybody looks this up, but even if we can't find it online, we could calculate it if we need to. And different people get, more particular. We could get more sig figs out of that if we want, but this is it. It's more like 21% oxygen. There's other stuff in there. All right, so how are we going to do this problem? So let's go through the calculation. If I have 1 pound of methane, then it's the same situation. I want to go from pounds of methane to, well, actually, why don't you guys go ahead and see if you can string it together, and then tell me how many pounds of air are required to do this. Actually, let's see. Let me do this because I have some time constraints here. So we'll go pounds of methane to grams. 453.6 grams per pound. And so the pounds cancel. That leaves us with grams of methane. And then we can go from grams of methane to moles, 16.05 grams for 1 mole of methane. So the grams of methane cancel. Oops, that leaves us with moles. And then we're going to go to moles of oxygen. All right, here we could use the 22%, or we could continue on to grams and then use the percent by mass. So here we come to a branch. In this particular branch, I'm going to use the mass, but in other problems, I might just go ahead with the moles. And so we could say for every 100 moles of air, there's 22 moles of oxygen. I could do that, but what we're going to do is we're going to go straight to mass. That is 32.00 grams of pure oxygen per mole of O2. And then I'm going to use the mass percentage there as a fraction or conversion factor. That is 24. For every 100 grams of air, there are 24 grams of oxygen. So this is given or calc. Oh, right. It would be 2 moles of oxygen for 1 mole of methane. That's from the balanced chemical equation, CH4 plus 2 O2s. So I made a mistake there. Thanks for that. All right, so now we have how many grams of air, and so the last step is to convert that to pounds. And this will tell us how many pounds of air we need. And so it's going to be the 453.6s cancel, moles of O2 cancel, grams of O2 cancel, grams cancel. That leaves us with pounds of air. And so this will be 32 times 100 divided by 16.05 divided by 24. 8.307 pounds of air. I only have 2 sig figs because I didn't pinpoint the composition of air so accurately. And so we're just going to say 8.3 pounds of air will meet for this. Does that make sense? All right, I'm going to stop here for the chapter 10.
Could we have branched out and used moles instead, like after we get the same?
Yeah, we could have branched out. Here, right here, we could have branched out. In other words, what we'll do is we'll come down here and then multiply this by 100 moles of air per 22 moles of oxygen. And so in this case, moles of oxygen cancel, and that leaves us with moles of air. But the problem now is we got to figure out how much does a mole of air weigh? How much does a mole of air weigh? In other words, what's the molar mass of air?
Well, they have 78 mole nitrogen and 22 mole oxygen. And then
Close, yeah. We could figure out the molar mass of air. That's another calculation. And so the next step here is we need the molar mass of air. Do you know how to get the molar mass of air? And so let me just do that calculation here. I was going to do this next time, but do it now. Molar mass of air. So I need to figure out for 1 mole of air, how many grams of air do I have? And what I'm going to do is I'm going to use the mole percentages or mole fractions. In other words, what I'm going to do is how much of that 1 mole is oxygen? Well, 22 out of 100. In other words, 0.22 moles of oxygen. And how much of that 1 mole is nitrogen? 0.78 moles of nitrogen. How much does 0.22 moles of oxygen weigh? Well, we know that it's 32.00 grams per mole. And how much does 0.78 moles of nitrogen weigh? Well, that's times 28.02 grams of nitrogen per mole of nitrogen. And then we add these up. When we add this up, that gives us the grams of air. And then we have the molar mass of air. 1 mole of air weighs this much. Does that make sense? Yeah. So I was going to do that next time, but since you asked, we'll do it now. And so we could have branched out there. We go from moles of air to grams of air, and then grams of air to pounds of air, and then we're done. We'll get the same answer. All right. I have to leave early today because I have an appointment I have to go to, but what I'm going to have you guys do is complete the quiz from the water quiz last time. And so here you have to do a lot of this stuff. Do we do a mole to mole, or do we do a gram to gram? What do we do as far as conversion factors go? So if you haven't finished the quiz from last time, go ahead and finish that now. And then what I'd like you to do after that is to work on the old exam 2 and old exam 1, and do the relevant questions there. If you get stuck, maybe you can get some help from others in the class. And the key's not out, so if you get an answer, you should check your answers with other people. And in science, we don't normally have an answer key, because in science you're doing a calculation that people haven't already done yet. And so what we do is we do peer review. Peer review is you check other people's work, make sure they didn't make a mistake. Because the first step in peer reviews, are other people getting the same answer as you?
Speaking of peer review, I think for the pounds of air, it should be 16 questions. The 2 moles, I think we still multiply by
You multiply by 1.
pounds of air.
Yeah, because there's a mole.
Oh, I forgot to do the 2 there. Okay. 16.6, thank you. See, that's peer review. So if I didn't have the answer key, how would I have known that? Well, other people can check your work. So we got 16.6 pounds. Thanks. That's a lot of pounds. So let me go back and look at my calc. Yeah. So what I'm going to do, I'm going to end it